Welcome to the 18th lecture in the open course on diffusion in multi-component solids. We will be solving diffusion equation for non-steady state diffusion. Particularly for infinite boundary conditions, we will make use of Laplace transforms, and hence this lecture is a refresher on Laplace transforms. So, one of the most important aspect of phenomenological expressions of diffusion is that we can use it to predict concentration profiles in different diffusion problems, right, with respect to different boundary conditions and given initial conditions. We can solve the diffusion equation to get the or to predict the concentration profile as a function of x and t. For that we need to solve the diffusion equation. Remember how we derived diffusion equation? So, we used a continuity equation, substitute fixed law expression into continuity equations, and we get the desired diffusion equation. Now, in steady state condition, the concentration at a given x does not change with time, and we have seen the solutions for steady state condition. We solved the diffusion equation for steady state condition. Now, we will go over the solution for diffusion equation in non steady state conditions, right, for different boundary conditions, initial conditions. For that we will use Laplace transform as one of the very useful mathematical tool. Now, you guys have already studied Laplace transforms in your mathematics class probably, but at that time the connection may not be very clear. The application of that mathematics to the problems that we solve in our material science or metallurgy may not be very clear. And so, I would like to first give a refresher of Laplace transform. So, next couple of classes I will give you the refresher on Laplace transform, because we will be using that very important mathematical tool for solving diffusion equations. Okay. So, anybody remembers what is Laplace transform? What does it do? So, how do we define Laplace transform?
It will convert one kind of function into another kind of, it will change the variable.
Okay. So, what kind of variable we typically use? Okay. So, let us look at the definition of Laplace transform, right. So, if we have a function f of t, then we define the Laplace transform of f of t, or we write L of f of t as integral from 0 to infinity e to power minus k t times f of t dt. So, if we have a function f of time t, to take its Laplace transform we multiply the function by e to power minus k t and integrate the product from time equal to 0 to infinity. So, this is a definite integral. So, obviously, it is independent of time. So, the Laplace transform is also denoted by the function f bar, and now f bar is not a function of t, but function of k. If we take the inverse of f bar of k, inverse Laplace transform, we get back the original function f of t. We write L inverse of f bar of k is equal to f of t. So, basically the function which was initially a function of time is, by taking Laplace transform, we are making it independent of time, independent of t. So, let us see some simple examples. So, suppose f of t is some constant p. So, we can write a Laplace transform of f of t is equal to integral 0 to infinity e to power minus k t times p dt, and p is a constant. So, we can take it out of integral 0 to infinity e to power minus k t dt, and integral of e to power minus k t is minus 1 by k e to power minus k t. So, minus p by k e to power minus k t from 0 to infinity minus p by k e to power minus infinity is 0, e to power 0 is 1, and so you got L of constant p is equal to p by k, or you can write L inverse of p by k is equal to p. Right. So, we will write down some of the Laplace transforms here on the right side. So, f of t and Laplace transform of f of t. So, if our f of t is p, Laplace transform of f of t is p by k. Consider another example. If f of t is equal to e to power pt, then Laplace transform of f of t would be 0 to infinity e to power pt times e to power minus k t dt e to power minus k minus p t dt. So, this integral will be minus 1 over k minus p into e to power minus infinity minus e to power 0. So, it should be equal to 1 over k minus p. So, if our f of t is e to power pt, its Laplace transform is 1 over k minus p. Similarly, we can look at another example. If f of t is equal to cos omega t, so let us try to get the Laplace transform of this. F of t is cos omega t. So, the Laplace transform will be integral 0 to infinity e to power minus k t cos omega t dt. So, let us integrate by part. This is the formula for integration by part. Integral u dv from a to b is equal to u v from a to b minus integral v du a to b. So, here we can write our du or our u as cos omega t and dv as e to power minus k t dt. So, obviously, du is minus omega sin omega t and V in this case will become minus e to power minus k t by k. So, if you take the derivative of this, it will be minus k e to power minus k t divided by minus k. So, it will get back this one. Okay. So, L of f becomes u v minus 1 by k e to power minus k t times cos omega t from 0 to infinity minus v du minus 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 plus minus integral 0 to infinity. This will be 1 by k, omega is also there, omega by k e to power minus k t sin omega t dt. So, this should be e to power minus infinity is 0 and e to power 0 is 1 and cos 0 is also 1. So, this becomes 0 minus 1 is minus 1. So, 1 by k minus omega by k. Now, again we integrate this also, we integrate by part. So, in this case we have u is equal to sin omega t and dv is equal to e to power minus k t dt. So, du in this case is omega cos omega t and v will be again minus e minus k t by k. So, minus omega by k times u v. So, this is written as u v is minus 1 by k times e to power minus k t sin omega t from 0 to infinity minus minus plus v du will be omega by k integral 0 to infinity v du e to power minus k t cos omega t dt. So, this should be equal to 1 by k and e to power minus infinity is 0 and sin 0 is 0 here. So, this term is 0. So, this should be equal to minus omega square by k square, and this is again nothing but the Laplace transform of function f is equal to L of f. So, if we take L of f common on this side, so we will get L of f times 1 plus omega square by k square is equal to 1 by k, and so I get Laplace transform of f should be equal to k over k square plus omega square. K will cancel and this will come down. Okay. So, the Laplace transform of cos omega t we obtain as k over k square plus omega square. So, we can obtain Laplace transform of sin omega t similarly, and if we work on sin omega t, we will get Laplace transform of sin omega t as omega over k square plus omega square. So, we can obtain Laplace transforms of some simple functions similarly, and you will see they are tabulated at various places. So, these were simple functions. Now, if we have to deal with complicated functions, then we need to look into more properties of Laplace transforms, right. So, couple of them are, one is the linearity property, right. So, states that Laplace transform of A times f1 of t plus b times f2 of t is equal to A times Laplace transform of f1 of t plus b times Laplace transform of f2 of t. The second property, which is called k shifting property, the k shifting property essentially says that if f bar of k is Laplace transform of some function f of t, then Laplace transform of the product of f of t with e to power p t is f bar of k minus p. Okay. So, it is shifting the k, and that is why it is called k shifting. If we take inverse, L inverse of f bar of k minus p will be equal to e to power p t times f of t. We can prove this. So, if we write the Laplace transform expression for e to power p t times f of t, it will be integral 0 to infinity e to power minus k t times e to power p t f of t dt should be equal to integral 0 to infinity e to power minus k minus p t times f of t dt, and if we substitute k minus p equal to s. So, we get L of e to power p t times f of t is equal to integral 0 to infinity e to power minus s t f of t dt, and this is nothing but again similar expression to Laplace transform of f of t. So, this would be f bar of s, and s is nothing but k minus p. So, this is f bar of k minus p. So, for example, if you consider any function from here, let us say sin omega t, then the Laplace transform of e to power p t times sin omega t should be, it should be this, looking at that table. Yeah, you have to substitute k with k minus p. So, that should be equal to omega over k minus p square plus omega square. Similarly, what will be the Laplace transform of e to power p t times cos omega t? You have to substitute k with k minus p. So, it will be k minus p divided by k minus p square plus omega square. Now, this property especially becomes handy when we are trying to find inverse Laplace transforms of some complicated function, right. So, let us see one example. So, let us try to find inverse Laplace transform of a function. So, f bar of k k is 6 over k square plus 6k plus 18, right. So, how do we go about this? So, this we can write as k square plus 6k plus 9 and this is nothing but k plus 3 square. So, and 6 can be written as 2 times 3, k plus 3 square, and 9 is 3 square. So, does this look familiar? So, L inverse of f bar of k should be equal to 2 times L inverse of 3 over k plus 3 square plus 3 square. So, this looks similar to the expression for sin omega t, expression for Laplace transform of sin omega t with omega equal to 3, and instead of k we have k plus 3. So, we use the k shifting theorem. So, this should be 2 times sin omega is 3 times e to power p t, and p in this case is minus 3, e to power minus 3t. Clear? So, this is how we can get the inverse Laplace transforms too. Okay. So, now we will be solving differential equations with this. So, we are also interested in Laplace and inverse Laplace of derivatives. Okay. So, let us look at the properties of Laplace transform of derivatives. So, there are two formula. So, Laplace transform of f prime will be k times Laplace transform of f minus f of 0, and the Laplace transform of second derivative of f, that is f double prime, is equal to k square times L of f is k times f of 0 minus f prime 0. So, again let us try to prove this. F prime, since f is a function of t, f of t. So, f prime is nothing but df by dt. So, Laplace transform of f prime would be equal to integral 0 to infinity e to power minus kt df by dt dt. Now, how do we proceed? Integral u dv, right. So, we integrate by part. So, in this case our u is equal to e to power minus kt and dv is df by dt dt. So, du here will be minus k e to power minus kt, and v in this case is f. So, uv would be f into e to power minus kt from 0 to infinity minus v du minus minus plus k integral 0 to infinity e to power minus kt into f of t dt. Okay. So, L of f prime, this is nothing but, this integral is nothing but Laplace transform of f. So, should be equal to k times L of f plus, and this at t equal to infinity this is 0, at t equal to 0 this is 1. So, f into 1. So, this is basically f at t equal to 0. So, f of 0. So, this becomes minus f of 0, right. So, this proves our first formula. For the second one, it is simple. If we have the first one, because f double prime is nothing but f prime prime. So, we just substitute L of f double prime is equal to k times L of f prime minus f of 0, again substitute for L of f prime, should be k times L of f, this should be f prime 0, L of f minus f of 0 minus f prime 0. So, L of f double prime should be equal to k square times L of f minus k times f of 0 minus f prime 0. So, this proves our second formula. So, we can use this to find again Laplace transforms of more complicated functions. So, let us see an example. Suppose we have to find the Laplace transform of t times e to the power pt, right. So, my f of t is equal to t times e to power pt. So, obviously, f of 0 here is 0, f prime here will be e to power pt plus pt times e to power pt. So, f prime 0 will be e to power 0 is 1 and this will be 0 1, and f double prime will be p times e to the power pt plus p times e to the power pt plus p square t e to the power pt. So, this should be equal to 2p e to the power pt plus p square t e to the power pt. And if we use the second formula here, we will get Laplace transform of f double prime should be equal to 2p e to the power pt plus p square t e to the power pt should be equal to k square times Laplace transform of f, and f here is t times e to the power pt minus k times f of 0 is 0 minus f prime 0 is 1. So, what we get is if we take L of t times e to the power pt and p square times L of t to the power t times e to the power pt, if we take it on this side, so we get k square minus p square times L of t times e to the power p t is equal to 1 will come on this side 1 plus 2 p times L of e to the power p t, and L of e to power p t is 1 by 1 over k minus p. So, 1 plus 2 p over k minus p, which is nothing but k minus p plus 2 p is k plus p over k minus p. If we write this as k minus p times k plus p will get cancelled, and so we get Laplace transform of t times e to the power p t should be equal to 1 over k minus p square. Okay. So, we can write another formula here, Laplace transform of t times e to the power p t as 1 over k minus p square. I will stop here today.